Today's presentation is offline reinforcement learning. Before we can talk about the offline part of reinforcement learning, let's give a little background about reinforcement learning. I'm assuming a lot of you have heard about the recent breakthroughs in reinforcement learning, from DeepMind's solution to the game of Go, where they beat world-class champions in the game of Go, and also different solutions of computer games such as Atari Suit or Minecraft or even StarCraft 2. Very big and complicated games. And also breakthroughs in robotic manipulation tasks. The things that maybe a couple of years ago you would think are just imaginary are today solutions of reinforcement learning. So what is reinforcement learning? The subject of this presentation will be offline reinforcement learning, but what is reinforcement learning in general? So the basic framework consists of two entities. We have an agent, right? The agent could be, for example, you or the player or an actual robot or an algorithm. And we have an environment. So an environment is for example, a chess game that we're going to play. Okay, so environment could be anything that we want to interact with. And the way the whole process works is through this feedback loop where when environment starts at some state or at any time t is at some state s. So if we take the example of the chess game's current state is the position of each one of the pieces in the chess game, right? The agent, or the player for that matter, can take an action in this environment. Taking an action in this environment would mean moving, for example, a piece in the chess game to another spot on the chessboard. And this would transition the current state of the environment, in this example, the chess game, would transition this state to a new state, and then this process would go on again and again, and we would take more action. What the environment gives back to the agent after each action the agent takes is two things. One is an observation. The observation could be the actual state of the environment. So it could be the actual state of the chess game, for example, the position of all the pieces. But it could also be any different correlated observation of the current state. So maybe we have a video camera taking footage of the chess game from the side, from a third-person perspective, and that would be an observation of our state. It's not the actual state. Maybe we don't see the full state even when we look through this camera, but it's an observation of the state. So an observation is something very abstract that gives us some notion. We also get back from the environment a scalar reward. So the reward tells us how good the state that we're in actually is. And our mission is going to be to try to maximize the cumulative rewards that we get. We want to get as much high rewards as we can. In an example, for example, if you think of a navigation task, for example, when you have to get from point A to point B, so one reward that we could define is giving a reward of 1, for example, reaching our target, and 0 otherwise. So that could be a reward function that we could give to maybe a robot that tries to navigate an environment. Okay, so that's an example for a reward function. So here on the bottom right, you can see an example of what an agent might look like. So an agent might be a neural network that gets as input observations and outputs actions to do in the environment. We want to find a neural network, perhaps, that would be optimal in some sense. And we'll talk about what optimal means in just a second. So the basic framework that reinforcement learning relies on is Markov decision processes, MDPs. Here I'm going to give you a more general scenario, a more general framework, which simply assumes a partially observable case. And I'm giving this a framework because it's actually the more general and more practical one. I mean, in general, we can't assume that our environment is fully observable. We can't assume that we really see the full state. Most real-life scenarios are actually partially observable, even though most algorithms don't assume partial observability. How is this defined? What is a partially observable Markov decision process? POMDP for short. It's defined by a state space. So in our example with the chess game, it's the state of the board, the current state of the board. An observation space. So this is some kind of observation of the state. And we have our action space. These are the allowed actions to take in the environment. We also have a reward function. This is something that is usually defined by us, by the ones that want to solve a specific task. We define some reward function. This is going to try to optimize. There's also some kind of transition function and observation function. So these are not necessarily known to us. So maybe in a chess game, we do know what would happen if we take an action, But in the general world, we might not really know exactly what would happen. So for example, if your environment are users in some kind of, I don't know, maybe you're trying to market to some users, then you don't really know what would happen if you show a user an advertisement. So this could be a transition function that is not known to us. So the transition function is something that brings us to a new state if we take an action A. So in the chess game, that would be if we move a piece in the chess game, we move to a new state of the board. Okay, so we have a transition function. We also have an observation function, which with some probability shows us a certain observation given that we're in a specific state. And in MDPs, unlike POMDPs, in MDPs, the state space and the observation space is the same thing. In general, you can think about MDPs because this is what we'll usually talk about. But it's important to remember that in the general case, we don't really always get to see the actual state space. We see only observations of the state space. So this is the basic framework we're going to rely on. Now, what does reinforcement learning try to do? So now we turn to the agent side. The agent side, remember, we are the agent. We are the algorithm that's trying to get as many rewards as possible. We have a policy. Okay, a policy is simply a mapping between all the histories or all the observations that we've seen up until now. It could be also just from a mapping from the current state that we see to an action. We see the current state of the board, and we need to choose what action we want to choose. Or maybe we saw all the observation leading up to this state, and we want to choose an action to do. Okay, so this is what we're going to try to optimize. This is our policy. We also have something called a discount factor. It's a number between 0 and 1. We'll see what this means in a second. And we have our value. Okay, so the value is actually what we're going to try to maximize in a second. The value is the expected cumulative sum of discounted rewards. Okay, we want to maximize we want to get as many rewards as possible. This discount factor that you see here, the gamma to the power of t, tells us that maybe sometimes, if gamma is less than 1, we want to, are nearer to us in the future are more important to us, are more important. Okay, and rewards that are farther away might not be as important to us. But in general, you could even take gamma equal 1, and then what you're trying to do is maximize this sum of rewards. Okay, so this is the value. Another important quantity or function is the Q function. It's also known as the state action value. And it's very similar to the value function, and this is and this function is something that is going to you're going to see it a lot throughout this presentation. This Q function. So it's important that you understand what it means. The Q function, unlike the value function, asks the question: what would be the value of policy pi if I were to execute pi, but at the current state take action A? So the value asks what would be the value, what would be the sum of rewards if I use policy pi, but the Q function lets us take a different action at time t equals 0, meaning at the current state, it lets us take a different action, and it asks the question, what would be the value then if I take a different action at this state? So in this case, the action would be A, and then after taking action A, I would execute policy pi. So that would be the Q of pi at S and A. Okay, so this is a very important quantity. Again, the goal of reinforcement learning is to maximize the value. So we want to find the policy that would maximize the value out of all policies that we were looking at. That's the goal of reinforcement learning. So here's some useful relations. First of all, I told you that the value and the Q value are quite similar. So the value looks at the expected sum of rewards under policy pi, and the Q function looks at the expected sum when we assume that at the current state we're taking an action A. So the value and the Q function are actually related in the manner that you see there. It's simply the expectation given that A was sampled from pi. So they're very much related. The Q function gives us a little more control over choosing a policy, algorithmic control. And we also have the Bellman equations, which are quite important. They let us estimate and approximate the Q function. So we can write the Q function using the Bellman equations as you see there. The Q function is R plus gamma, the value of the next state, the expected next state. Okay? So these are relations that will let us algorithmically bootstrap the value and learn the Q function using data. Okay, so here's one type of algorithm for reinforcement learning that can be used. Let's say we take the Q function. The Q function is also sometimes called the critic, and the policy pi, sometimes we call it the actor. So this is the actor-critic framework, and it says the following. It says take a parametric critic. So for example, you represent the Q function by a neural network. So you'd have a neural network where you input the state and the action, and the output of the neural network would be the Q value of that state and action. And you also have an actor, which is a neural network that would maybe get as input the state and needs to output a probability over actions. Okay, so we want to find the best Q function and the best policy, the best actor. I want to optimize these neural networks. So we can follow this two-step procedure. First, we would minimize the Bellman error, right? So I told you that the R plus gamma value of the next state is another way to write the Q function. So if we have data of states, actions, rewards, or next state, then we can solve this, right? We can use this loss to minimize this squared error and get a good estimate for the Q function. And then after we do this, we could try to maximize the policy that would maximize this current Q function. So we would take one step towards maximizing the policy. So we would take a gradient with respect to the second loss over there, number 2. And we would repeat this process. Again, we would fit the Q function. And again, we would find a policy that would maximize this Q function. And again, we would fit the Q function, and so on and so forth. Okay, so it's type of an EM algorithm, which would converge to an optimal policy. Okay, so this is the actor-critic. So again, this is not a presentation about reinforcement learning, but rather a much more recent field of offline reinforcement learning, which is going to use only offline data in order to optimize our policy, to find a good policy. And unlike online reinforcement learning, we're not going to be assuming that we can do online interactions. In fact, we're going to assume that some other agent that is not us generated the data for us. And this is going to be very problematic for us. So how is the data going to be generated? We have some agent, maybe it's a doctor and a physician that is taking actions giving treatments to his patients and logs the actions and the states that the patient was in and the treatment that the physician gave the patient. So this is the data generating process. We start at some state. The policy, the physician for this matter, is also known as the behavioral policy. We denote it by pi b, is going to take an action A0 at state S0. It's going to receive a reward. Afterward, the environment will transition to state S1. An action A1 will be taken, and a reward R1 would be given. Again, the environment would transition to S2. An action A2 would be taken, and a reward R2, and so on and so forth. So again, this pi b, this policy that chooses action, is not us. It's some other behavioral policy that we don't get to control. We might not even know this behavioral policy. We don't know how it chooses actions, but it's going to generate states, actions, and next states for us. That is going to be our data. So another look at it is through trajectories, right? A trajectory is a sequence of state, action, next states, state, action, next states, a full trajectory of such things, and rewards, of course. So this behavior policy is going to generate one trajectory and another one. Maybe that's of a different patient, if we're thinking about a physician, and maybe another trajectory and another one. And in the end, we're going to be left with this data set of trajectories or transitions that we're going to want to use to create a good agent that would interact with the real world in the end. But we're not going to have access to this real world. We're going to have access only to this data. Why is it so important to use offline data in reinforcement learning? So first of all, offline data is something that is really abundant. We have a lot of offline data in many problems. So if you think maybe like I said, the medical domain, that we have a lot of data there, even autonomous vehicles, we have enormous amounts of data there that we can use. So there's already a lot of data. There's no reason not to use it. Even more importantly than this, online interactions are probably something pretty problematic, right? You can't assume that you can simply interact with the world. For one, it might cost a lot of money and time, right? So think about maybe constructing an autonomous car. So taking a car and driving the world would mean you'd have to actually buy a car You'd have to put all the sensors on it, get some fuel each time you drive, maybe put a person with in the car to make sure that it doesn't drive over anyone, and would have actually pay a lot of money to do this, and it will be very time consuming to do this. So interacting with the world every time might be very costly, because one car wouldn't be enough. Of course, we need a whole fleet of cars in order to be able to do something. 1 second, a drink of water. So that's one. Other than that, it might be very unsafe to do online interactions, right? When we have data, we have no problem. Data is very safe. Don't hurt anyone. I wouldn't want a random agent to start giving treatments to patients and try to learn what is good to do on patients and what is not. Other than that, data is often in data we have actual pretty good behavior, right? So again, if we look at data from a physician, from a medical doctor, then probably this doctor knows what he's doing, and we can actually utilize this to create a policy or an agent that is pretty good to begin with before we start interacting with the world. So using the data might actually be useful when we have actually pretty good data. We can try to imitate this. So we have data in games, in healthcare, autonomous driving, smart city, education, robotics, and much, much more. So in general, we're talking about using the data and interacting with the environment, but here we're gonna look at the very pure setting of offline data, using offline data for reinforcement learning. We do not have access to any environment. Some other literature that is very much related, offline reinforcement learning is something quite new in the research community. But other research that is related is off-policy evaluation, for example. Off-policy evaluation asks the question of what would be the value of a policy given data. So I have data and I want to ask what would be the value of a different policy. So this is actually also a pretty hard question. Off-policy reinforcement learning asks the question how to use data while also interacting with the environment. So it's a little bit different than offline reinforcement learning, which only accepts data. In off-policy reinforcement learning, we're actually also still allowed to interact with the environment. It asks the question of what to do with offline data, which we know that is optimal. So if we have offline data that we have an expert playing in this offline data, we just want to imitate this expert. There's no reason to try to learn a better policy than the data, because we know the data is good, so we can just try to imitate it. Other than that, we have causal inference. Causal inference is very similar to offline reinforcement learning. The basic assumption there is that we don't see the full state, and when we don't see the full state, we get a lot of different and interesting problems of biases and identifiability problems, but this is not the subject of this presentation. So let's look at one example of a very basic algorithm that we might want to use. This algorithm, least squares policy iteration, it's pretty old, about 20 years ago, assumes a linear model, and we assume we can write the Q function as a linear sum of features, phi, that we get from somewhere. So here's the process. This is what the algorithm does. It first estimates these weights. Given that we have a policy pi, we start with some random policy, of course. Given that we have some policy pi, we estimate the weights of the Q function using least squares. Remember that I told you that we can use the Bellman error, right? The Q minus the R plus gamma V of the next state to estimate by least squares. So we can estimate the weights. After we have the weights, we basically have some estimate for the Q function. Then we can take what is known as the greedy argmax policy, right? The greedy policy is the policy which for every state takes the argmax of the Q function, the best action that the Q value tells me. So now this policy is not optimal, but it's better than the previous policy. I would take this policy and feed it back to step one. And again, solve the least squares and estimate the Q value of this policy. Now I would have a new Q value. And again, I would take the greedy policy. And I'd continue this over and over until I converge to the optimal policy. Now, what's the problem with this whole? First of all, it's a linear model. Of course, we know that many problems are not really linear. Here we need to know the actual features of the problem. Also, there are actually a lot of other problems here. Basically, one thing that is not even written here is that in the offline data, we don't really have necessarily have the data on the whole state space, right? We might only have data on a certain area of the state space. Other than that, we have a very big problem of an action distribution shift. Recall that in the data, it is not us that generated the data, but a different policy. Someone else generated the data. This means that when we're trying to solve the regression problem and solve for the Q function, we're actually having targets, our targets, y here. So we have f is the Q function that we're trying to optimize. Y targets here are actually sampled from a different distribution. Not only a different distribution, but a distribution that has a max operator in it. And I'm not going into these details, but this is very problematic for us. This distribution shift actually makes our Q function be too optimistic and cause errors.